Good morning, guys. It's 9 o'clock. Today is Monday, February 22nd. We are still dealing with Unit 1, basically, as far as the content for this class, basically fluid dynamics. And we will have a lab today. I think I posted already the instructions on Canvas. So we will be meeting later on today at 2 o'clock to discuss the lab. And also there is an assignment that is actually, I posted it actually for Unit 2, and that is before Chapter 15. And that is the quiz for this chapter, okay? So you guys need to really look at that quiz. The way this quizzes work is basically you'll have 2 attempts at them. You don't have a lot of questions. I think there are only 11 questions. They're conceptual questions. And so the time is adjusted accordingly, but you will have 2 attempts. And before taking the first attempt, please make sure you know the content, make sure you understand everything in the chapter, and then you take your first attempt. If you are still not comfortable with the grade that you got from the first attempt, you still have another attempt, but you have to understand that the system averages your grades. So you really have to review the content to make sure you bring up the grade. Otherwise, it's going to suffer. It's not going to take the highest of the grades. So the point being is that before taking your grades, make sure you're ready. Before taking your quiz, make sure you're ready for it so that you don't lose any points unnecessarily. But that is really to encourage you to go through the content and read through it and ask questions if need be, make sure everything is clear. So for chapter 12, we really have covered only 2 ideas so far, okay? Let me try to illustrate them. Let me share with you my screen to make sure that we know what we have covered. Share, and it's the OneNote from chapter 12. Okay, I hope you guys can see the OneNote in here where it says basically we're still dealing with the stuff from chapter 12. Correct? For some reason, it has shifted to the other side. Okay. Good morning, Lawrence. And okay, so basically, thank you. And basically, the 2 ideas that we have covered are the following. Where is my pen? Here it is. Okay. So the 2 ideas we have covered so far are, the first one, if I can find where my drawing pen is the fact that the pressure depends in a fluid, depends on where we are in it. The pressure on the same level is the same. So if the fluid happened to be here, like for example, when we discussed toward the end the U-tube, the pressure, at any given height, it's the same. So this P is the same as this P, albeit the fluid, let's say for example, the fluid can rise all the way to here. So in this case, on the same height, the pressure is the same. So that's what we proved earlier, okay? So that's what we did last time. So that's one thing. The other thing also is that the gauge pressure, it's very important to have an understanding that there is a difference between the gauge pressure and the absolute pressure. The gauge pressure is what is read at this point, okay? Versus versus a difference of some sort, okay? So for example, I have P1 in here, I have P2 in here. This difference in pressure is related to the height and difference, okay? And basically we arrive at that P2 minus P1 is equal to rho times G times the difference in depths, H2 minus H1, okay? So that is the value. In particular, we took the case when we are referencing the distances from the level of the fluid, this point in here, where we know, for example, on Earth, we have the atmospheric pressure. So if H represents how deep we are in the fluid, then the pressure at any depth is going to be the atmospheric pressure plus rho times G times H, where this rho is the density of the fluid. For the case of water, it's known to be 1,000 kilograms per liter, okay? Or if you wish, 1 gram per cubic centimeter, it's the same thing, okay? Did I say, no, per cubic meter, I'm sorry, it's wrong, okay? 1,000, or it's 1 kilogram per liter, Okay, they're all the same. It's the same quantity. Okay, so that is basically the density for water. For density of other substances, we discussed them. Another density of particular interest that is worth remembering is that of the air. The density of air, or raw air, is roughly 1. It's about 1.29 grams per liter, or 1.29 times 10 to the negative 3 kilograms per liter. So it's about 1,000 times less than that of water. It's a lot lighter than water. So those are the two things that it's actually one thing. It's the pressure as a function of depth. The other thing that we saw also is that if I have an object and it's somewhat submerged or partially submerged in a fluid, it's going to be subject to the buoyant force. So if this object has a volume V, it's going to displace an amount of water that is V also. This is provided it's entirely submerged. If it's partially submerged, then it's fine. How much is submerged will be the volume. So this is the volume of interest in this case. So this is the volume submerged, okay? So in this case, we can find a relationship of this density of the fluid, no, density of the object versus the density of the fluid. In this case, the density of the object is most likely higher. That's why it's sunk in. Otherwise, if it's the same as that of the fluid, wherever we put it in the fluid is going to stay in the place. So this is the force of buoyancy as we discussed it, and it's equal to the weight of the displaced fluid. The displaced fluid has a density rho times the volume of the fluid that is actually displaced, this V, which is the same as this V, times G. So this is basically the buoyancy. I forgot the name of Archimedes last time, which is kind of stupid, okay? But this is also known Archimedes principle. He's the one who found it, and he came out of the bathtub here screaming, Eureka, Eureka, I found it, I found it, I found it, okay? So that is the stuff that we saw last time, okay? I promise that we're gonna do a problem based on at least this one, and I think we're going to tackle it. Anybody has any questions from what we did last time? No? So we're gonna look at problem, let me check, I think I said 98, I forgot what the number was, or 86 or something. Problem 86 from the book, okay? Problem 86 gives you a graph. Basically, let me describe what the problem is. Let me first of all open Excel because I really want you guys to have, let me move the Excel spreadsheet in here and move the screen in here and share with you the Excel file. Share. No, that's not share. Share the open Excel file. Because I really, when you come to this class, are you guys looking at the Excel file? Blank Excel file? Okay, very good. So it's a good idea. I mean, as engineers, this is one of the tools that you must know how to use. There are other tools that are far more advanced than Excel, but at least Excel is actually a very powerful tool too. So don't underestimate it. That's why we use it extensively in this class, and you really need to be at ease with it, okay? And if you are sitting in the other class also, we use it too in that class too. So this is something that you need to be comfortable with. And this is actually used also for exams too. So you need to really know how to use Excel. Because if I give you a bunch of data, you should be able to answer stuff quickly. That's what we do in physics. We use a lot of data and basically interpret it and things like that. So problem 86, it says you have a bucket. I'm going to start writing on this piece of paper, okay, the stuff. And I'm hoping that you guys, as you read problems, also develop this habit, okay? So what the problem says in here, it says I have a bucket containing an unknown liquid. So I'm going to write the symbol for the density for the liquid as rho, simply rho, okay? I don't know what the density is, so that's because we don't know it. You also have a cube-shaped block. So the block has a cube shape. So I'm going to draw a cube in here. of sides A, because it's cube. So all the sides are the same. I'm hoping that you guys are following from what I'm doing, because I'm actually doing it in here on this piece of paper. So I'm hoping that you guys are actually doing the same thing. So this has, oops, I did the same side. Okay, so this has a side. So from here, I know the volume of this cube, okay? The volume of this cube is simply A cubed, okay? Not only that, but they give us a value. It's 8 centimeters. So this is 8 centimeter cubed. 8 cubed times centimeter, so which is 8 times 8, 64 times 8, which is whatever that is, okay? So that is something that we know from here up to this point from here, okay? So what else do we know? Wooden block that you measure to be in each side, but you don't know the mass. So we don't even know what the mass is, okay? So for simplicity's sake, I'm gonna write the symbol rho W, making sure the W here does not stand for water, but stands for wood, okay? So those are my symbols so far. I guess if I bring it up close, it's gonna cancel it. My symbols so far for this problem. So I'm just using notations that is I can basically refer to in the calculations. First, you place the wooden block in the liquid and measure the height of the top of the floating block above the liquid. So this is what you do. You take the liquid and you put it in a big container. Maybe if I switch to the other camera, it's easier. Yeah, I think I'm gonna switch to the other camera. That way you can see my writing and at the same time follow the Excel file, okay? So let me, what is the video? First of all, choose this camera and let me remove the background, because usually when I choose that one, everything goes blank. Remove virtual background, make it none. Okay. Okay, here is the stuff so far, okay? So what I have done in here, I am going to assume that this is actually the level of the fluid before. So this is when I put the block now of sides A, okay? We measure now the fluid, of course, I mean, the block will submerge in it partially, and we're going to have this distance h, because they say from the top of the block, from the block to the top of the fluid. So this distance is h, okay? So it's not 8 centimeters. It's something less than 8 centimeters, because this whole height is 8 centimeters. So when it's partially submerged, part of it is below, and the other part is h. So that's basically what the problem is saying in here, okay? So if you want to follow through, this is the notations that I'm using in this problem in here, okay? And what else do we need in here? Then you stack various numbers of US quarters coins onto the block and measure the new value of H, okay? So we put quarters in here on top of it, and each time we put 1/4, of course, because there is an added weight in here, so we're going to need more buoyancy in here. So FB needs to increase. That means we need to displace more water. That means this whole thing needs to sink a little further. So the more it's going to sink, the more water is displaced, and this thing stays in balance. So basically, the weight of the wood in this case, so it's the mass of the wood, which I gave you the symbol rho W, times the volume of the wood, which is this number, times the volume of the wood, times G, that is the weight of the wood. Because rho times V, that's the mass of the wood, times G, that is the weight of the wood. Now added to it the weight of the quarters, okay? So what I'm gonna assume in here that each quarter has a mass m0. So if I have an unknown number of them, let's say, for example, I have an X, so I have an X times m0. So that is going to be an additional weight, X times m0 times G. Those two weights must be canceled by the force of buoyancy if this thing stays in its place. If this thing does not go anywhere. So this is equilibrium condition, okay? The sum of the forces that are pointing down are going to be canceled by this force of the buoyancy, and the system stays in equilibrium. Now, the force of buoyancy is equal to the weight of the displaced fluid. So this is how much weight has been displaced And for that, I'm going to use the rho of the water, which I assume to be rho, okay, from my notations, not water, the fluid, I don't know what that is, times the area A, because it's all of it coming from this area, okay, in the bottom in here. So that's how much we're pushing in here. So times the area times the displaced fluid. Remember, initially it was 8, okay? It was A, okay? And now it's less of it by H. So it's A minus H is the actual amount that is displaced. Because if I have an A originally, and then partially of it is submerged, so that this distance is H, so the submerged in here, the displaced fluid has a height of A minus H, okay? Because this entire thing is A. So now times A minus H, that gives me the volume of the fluid that was displaced, okay? A times the difference in height between the entire length and how much fluid, how much the block is still above the fluid, that gives me the volume of the fluid that has displaced, times the density of the fluid, that gives me the mass of the fluid that has been displaced. Of course, times G. This is the force of buoyancy, okay? This two must be equal to one another. So basically, this two forces, the force of buoyancy and the two weights, the weight of the quarters and the weight of the block of wood, which is the density of wood times its volume, must be the same. So basically, this is the relationship that I'm looking at in here, because they're going to give us a bunch of data and we need to draw this dependency. So basically, this is the expression. I have X amount of quarters, and X amount of quarters there in the X axis, they are in the independent variables. Okay, so X in here is the number of quarters. Just a number, like initially it's 0, then 5, then 10, then 15, then 20, then 25. Times the mass of each quarter. When I looked up I Googled it, that's all, okay? So any website will give you the number. So the cent weighs about 2.5 grams and the quarter weighs 5. So M naught is actually 5.670 grams. Okay, that's basically what the, which site is that? usmin.gov, okay? I think they refer you to use that website, don't they? Yeah, that's exactly what I got it from, okay? So that is the mass of the quarter times, of course, G. This is the weight of all of the quarters because I have X amount of them, plus the weight of the wood, which is the density of the wood times the volume of the wood times what else? Times G, okay? Must be equal to the buoyancy force in this case, and the buoyancy force in this case is the density of the water, the fluid, times the area of the box itself, the block itself, times the amount that is submerged only, which is A minus H, times G. Okay, obviously G cancels everywhere, so we could do this experiment on the moon, and it's the same result would occur there. So it doesn't matter where we are going to get the same result. Okay, but we have to have some G, otherwise this will not work. Okay. Okay, so now we're going to find H now, because we have H as a function of X, where X is a number, dimensionless number. It's just a number, okay? It's not a position or anything like that, okay? So what we do in this case is we move things around and as a function of this number. So we're going to move the H to this side and we move the X and everything else to the other side. So I have rho AH, rho times A times H, is equal to rho times A times A. And I have equal plus minus, because I moved this one to the other side, it's rho W times V. And of course, I got rid of the G, so I'm not worried about that. Minus X times M naught. If I divide by this number everywhere, I'm going to find H to being simply rho times A minus rho W times V divided by rho times A and minus M naught over rho times A times X. Okay, so this is basically the function I'm looking at. Okay, it has a y-intercept, which is this value, and it has a slope, which is coming from this expression in here. Okay, so this will be the slope, and this will be my y-intercept. So that's how this function is. It's just a line as expected, as the graph shows. It's like this one. So that's basically what I'm looking at. So this is the y-intercept. It's this value itself. Okay. So the y-intercept, if you look at the graph from here, it's 3. I have to use some units that I have to be careful with in here because the units matter. If I keep h in centimeter and a is in centimeter squared, then a is in centimeter, and I have rho, if I leave v as in centimeter cubed, the units for rho naturally in this expression will be grams per cubic centimeter. Let me explain why the grams in here. The grams will cancel everywhere in here. Okay, because I have grams in here, I have grams in here, I have grams in here. I have grams per cubic centimeter in here times centimeter cubed. Wait a minute, there is something in here that is not, did I miss an A somewhere in here? No, that's fine, okay? Because I have grams per cubic centimeter times centimeter squared, so I have 1 over centimeter left in here, which goes all the way upstairs in here and becomes a centimeter. So dimensionally, this would ensure the units. This will be just a grams in here because I have grams per cubic centimeter and I have cubic centimeter. They cancel, I will be left with a gram. That cancels this gram. Same thing in here. I have grams per cubic centimeter times centimeter squared. So I'm left with 1 over centimeter times another centimeter in here. So the centimeter and centimeter cancel. I'm left with a gram in here. So the gram and a gram divided by gram, I got rid of all of the grams. Now I'm left with 1 over cubic centimeter times centimeter squared. So I'm left with 1 over centimeter. And when I bring it up, it's going to be centimeter. And here, X has no units because it's just a number. M is in grams. And in here, it's in grams per cubic centimeter. The grams and the gram cancel. Cubic centimeters, and I have also centimeter squared, which come upstairs, and the units match. So the dimensional analysis, this expression has no problem with it. Provided H is in centimeter, and this number X is just a number, has no units, and rho is going to naturally fall in grams per cubic centimeter. Okay, so whatever we find for rho is going to be in grams per cubic centimeter. So hopefully you guys have no problem with keeping the units the way they are. Therefore, this answer in here, rho times A minus rho of the water times A, because the volume, if you guys remember, although it's cube, it's easy to see why. So this area is A, that is actually sinking the block, and this height is A because it's a cube, so it's the same thing in here. I just want to simplify and get rid of this A in the denominator, so divided by rho A, so the A cancels everywhere in here, okay? And as a matter of fact, this expression then becomes, this is 3 centimeter, by the way, 3 centimeter is equal to rho minus rho of the wood divided by rho times A. So from this expression, I have some relationship between these rows, okay? Remember, A is 8 centimeter, okay? So I have 3 over 8, where the units cancel, and I have in here 1 minus rho of the wood divided by rho of the objects is equal to 3/8. So from here, I can find that there is a relationship between rho of the wood over rho of this object, of the fluid, is equal to 1 minus 3h, which is 5/8. And that is a result that is coming from the y-intercept. So I have a ratio of the two densities, okay? And this is before doing any kind of slopes or anything like that. Where is my, is everybody following so far? I hope that you guys, it's the whole argument has to do with these things in here, and whatever makes you feel comfortable with the notation is up to you, really. Once you reach this relationship, how you handle it is up to you. What you know from here is that this is your y-intercept, and I made this notation here to come up with this simple expression, the ratio of the two densities. which is rho of the wood versus rho of the fluid. Okay, because of this number in here being 3, it turns out that that ratio is 5/8, and it's coming from the y-intercept. Now I need to find the slope. So for the slope, I need to take the data and put it in an Excel file. Okay, I could do it basically just from these numbers, but I'm going to, because that slope will determine for me the value of this rho fluid. Because I told you guys that I just Googled the value of M naught, and it's 5.67 grams. And I know the area being 8 squared, which is 64. So if I know what this slope is, I can find what rho is. Once I find the rho of the fluid is, then I can come to this expression and multiply it by 5/8, and I'm already done with the densities in here for this problem. So let me plug in the numbers in here. It's clear. So in my Excel file, I'm going to refer to this one as being the X, which is just a number. And in here, I'm going to refer to it as being the H in centimeters. Make sure it's in the units in here are clearly stated so that I don't have to change anything. So when X is equal to 0, no quarters added, H is equal to 3. That's how much above the fluid we are. Okay, 3 centimeters above the fluid. So the more we put, the H is going to be less and less. So that means we're cutting down from so initially 5 centimeters went below the fluid. So now more and more of the fluid will be sinking in. I mean, more and more of the block will be sinking in. I'm sorry about that. So when I added 5 quarters, I'm going to estimate this one to be slightly more than 2.5. So I'm going to put it 2.6. If you want to, just 2.5 and see where that leads you, because I don't know if you guys clearly see the problem. If you guys have access quickly to it, you should see that it's slightly above the 2.5 mark, okay? Because they gave you a graph, they didn't give you data. So for 10, it's clearly more than 2 and less than 2.5. So I'm going to estimate it to be 2.25, okay? And then for 15, and that's really why I'm getting you guys onto Excel, because this thing could have different answers if you put the numbers differently. If you take a ruler, for example, and you start locating those numbers, which I'm going to do quickly in here with my ruler, so you can clearly see that it's for 15, for example, it's less than 2, but clearly way more than 1.5. So it's very close from 2. So I'm going to make it 2.8, okay? I'm sorry, 1.8. Between 1.5 and 2. And for 20, it's slightly above 1.5. So I'm going to estimate it to be just 1.5, okay? Slightly more than that. And then for 25, slightly more than 1, actually, for 25. It's clearly more than 1, but it's clearly a lot less than 1.5. So I'm going to make it 1.25, okay? 1.25 for 25. We're ready. So all we need actually is the slope. So we could plot this function, this data in here to see how it looks like, which is something that you'll be doing a lot in this class with the labs. So I'm going to go in here. So what is this thing in here popped up? So we're going to come in here and insert. And when we insert, we're going to find this graph will do. This one will do. Okay. It's not exactly aligned the way that they have it in the way they have it in the book, but it's close enough. So I can, from here, I can improve of my data in here. I can improve on my readings. I thought this one is slightly more than 2.5. Could have made this one 2.6, okay? And it brought it a little bit better than before. And I could do that adjustment to find what, and this error is going to be typical, okay? So this is part of your interpretation of this graph. So anyway, so let's see here. One thing that you could do to find the trend line is to actually add the trend line and make sure that that trend line is linear, okay? And more options. Let's see what, okay, why is my program? Oops. My computer all of a sudden, okay. More options. So we want trend line, and I can display equation on chart. And it gave me the slope in here being negative 0.014. Okay, there is another way of actually doing it without even plotting this whole thing. Okay, and that is you go anywhere in Excel, doesn't matter where you are, and you call it slope just to make sure that this is what you're finding. Okay, and you write in here equal to slope, and slope function is known function in Excel. It wants the y coordinates, the independent variable. This is the independent variable. I'm sorry, the dependent variable. And it wants x values, which are the independent variables. Okay, so the first one goes the dependent, the second one is the independent. Once you pass in this ranges, you're going to give you the value, which is negative 0.7143. Okay, word of caution about the Sig Figs. Okay, in this problem, there are only 2 Sig Figs. Excel will give you a lot of Sig Figs that don't mean much. So really, the value is 0.071, and that's enough. You cannot really make up more Sig Figs than that they are. Okay. So since we are in Excel, we can use Excel to find the value of rho. If I go back into my expression in here, and call this one the slope, okay? So the slope, which I'm gonna give it this, usually normally in math, the slope is given the symbol m, but because I already have a bunch of m's everywhere, so I'm gonna give it a different name in here. So I'm gonna give it the letter S for slope, okay? So the slope is going to be equal to minus m naught over rho A, rho big A, that's the area, I'm sorry, which gives me then rho from this expression equals to minus m naught over the S, the slope, times the area, or minus 5.670. I mean, I am keeping up more than needed in terms of Sig Figs in here, because this is a known value, okay? Divided by S, which is the slope, times the area squared, which is 8 squared. Keep everything in this unit system, and the answer should be in grams per cubic centimeter. So I'm going to come in here, and I left the minus sign because S is negative itself too, as you can clearly see from the Excel file. So I'm going to find in here and write rho, and I am going to write the same formula equals to minus part of the formula 5.67. It doesn't matter that you write a 0 in Excel, divided by open parentheses. The slope in here, I can write again the function, or I can just get the cell from D5, whichever you like, okay? I can do D5. That's gonna give me the same cell that I already computed with it. Or I can write the same function here just to make sure that I know what the function looks like. So I did not even have to do that step. This is the dependent variable, and then this is the independent variable. Okay, so this is my excess, my slope, times in the denominator is still 8 squared. Okay, so this is the value for rho, 1.24. Okay, technically it's only 1.2, again for the same reasons that I was making a fuss over, namely so rho is simply 1.2 because Sig Figs in here, the entire problem is just 2. Okay, so this is grams per cubic centimeter. It's not really rho for water, because rho for water, from what we talked about earlier, it's just 1 gram per cubic centimeter. So think of this fluid as being just that of a water with a lot of salt in it. Okay. Now, if you want to find the rho for the wood, all you have to do is multiply this number by 5/8 times 1.2, and that should give me, again, rho wood equals to 5 times 1.2 divided by 8. Okay. Oh, I did not put the equal sign. I put it actually in the wrong place. So cancel that. So it needs to be in its own cell if I'm doing a calculation, or I have to concatenate stuff. So it's giving me 0.75, again, grams per cubic centimeter. Okay. So this one is 0.75 grams per cubic centimeter. And that's basically the type of wood that we use in this case. And here it's less than the density of even water. So we expect this one will will sink in the water, let alone in this object in here, okay? So that's the problem in here. The mass of the block. Now we can find the mass of the block because all we have to do is multiply this rho by the volume. So the mass of the block is going to be rho times the volume, which is 8 cubed, okay? And it's going to be straight out in grams, okay? So if you're curious about the mass of the, did I write this one, EHO? I'm sorry, I don't know what that is. Okay, so the mass of the wood is going to be just the density of the wood, which is this expression, okay, times the volume, which is 8 cubed, okay? And it's 384 grams. To be more accurate, it's only 380 grams because that 4 is part of the Sig Figs that we don't know much about, okay? So, any questions about this problem? Let me switch cameras in here. Any questions about this problem? I know I went in detail, and I really wanted something out of it more than the actual problem, to be honest with you, and that is the Excel stuff that I want you to be at ease with it. Is everybody comfortable with Excel? At least so we're in here. Okay, task 1 of the day is that Excel is important for you guys, okay? So you need to really learn it as much as possible, and this course relies on it. So that's basically the prompt 1 of the day, discussions today, okay? Is everybody on board with what is expected? It's not more of a question than more of a task. That what we need to do as students, engineers, is to be familiar with something that can help us do these things. So I'm relying on you guys to emphasize on that, and hopefully we will have it with no problem, okay? So let's continue with the discussion of, I know that there is another problem that I promised that we will tackle, but we'll get into it hopefully before everything is done. So, where is the OneNote? Okay, so let me share with you again the OneNote. Let me move the this thing to the other screen, or keep it in the screen, it's fine. Share. So we learned 2 things. How the pressure depends on the depth in a fluid. And then the other thing that we learned also is the buoyancy, okay? And the lab is on buoyancy, okay? And the other thing that we're going to be talking about in here is Bernoulli's equation, which is a very big deal, especially in terms of doing calculations and so on and so forth, okay? So imagine with me, I have the following situation. Now we're not dealing with hydrostatics anymore. Actually, we're doing it with hydrodynamics. So we have a fluid that somehow is in flow. I mean, we're going to consider the simplest cases of the flow because fluid dynamics is a very complicated topic, by the way. It's probably the most complicated topic there is. But we're going to make it easy for us where the flow is a so-called laminar flow, where basically all the layers are going to be moving in parallel to one another, as if think of it as like layers of a sheets, basically. They are all moving in the same direction with the same flow. We're going to ignore viscosity because the fluid, when it's moving, it's actually going to attach to the sides of the wall and actually attach to the side to itself because of friction. So we're going to ignore viscosity. So we're talking about fluid that is non-viscous. Okay, if you're doing this experiment with, for example, honey, it's very viscous fluid versus, for example, that of water. So we're going to ignore the effects of viscosity, which is important. So we're going to ignore the other thing that we're going to ignore also is compressibility of a fluid. If you take fluid and you press it against itself, technically it's going to be compressible. So the fluid that we're going to be dealing with is also non-compressible fluid, okay? So we made two major sacrifices from what the real situations are. So that's how we do things in physics. We make things as easy as possible to begin with, and then we start to come up with different conditions for it. For example, if we're going to try to discuss, for example, weather phenomenon when there is big chaotic behavior, then we are at the turbulent level. At that point, we are completely in the other extreme of the situation. We are not in a laminar flow. Actually, we're in turbulent flow. So in this case, we have to have completely different situations. Some of these things also becomes negligible, and then we start to talk about other things. So at this point, we're just talking about the easy part of it, that you have a fluid that is moving. You are far away from the edges of the fluid where it's in contact with the material where it's flowing, and you're looking at the layers as they are moving, all of them moving with the same velocity. Otherwise, in a fluid where that is a real fluid, so if this is the wall of the conduit, then the flow in here will be much higher than the flow in here, which is actually not moving at all in here, because if I'm going to ideal the situation here, so the velocity starts to increase until it reaches this velocity, until I am back into the sides in here. So the flow in the middle will be a lot higher. But we're going to ignore that. We're going to focus only on this side in here of the fluid, where the flow is going at a constant rate, okay? At least for this section. If I'm looking at a different cross-section, obviously I have a different problem in here. So in here, the fluid will find a much higher place to flow. So it's going to have probably a different rate, which brings me to the first concept in here. If the fluid is not compressible, then this is what's going on in it. So I'm going to take a conduit in here of some sort. Oh man, I did it wrong. Okay, again. Intent for it to have two different cross sections. It's clear A2 is a lot less than A1. Sorry about my drawing, okay? Can't draw on the surface in here, especially with the dirt on it. It gives me kinds of problems, and probably I need to change the tip anyway. So clearly, what I think of it, that you have big, you have a tube on one side that's a lot wider than the other side. For example, when you go outside and you take the hose and you try to hose things, if you squeeze on it, of course, the water is coming from one side on a smaller cross section than from the first side. Okay, so let's think after 1 second. 1 second has passed. Okay, let's say, for example, the fluid that was in here has moved to this area in here. By a distance, I'm going to call delta x. On this side, it's delta x1. On this side, because the fluid is not supposed to be compressible, it has moved clearly much higher, because the same fluid must come from the other side. Okay, so it has moved the whole distance, which is delta x2. So this is the fluid that came out. Okay, because I'm assuming that the fluid is not compressible, so which means that it doesn't collect itself in one space. Okay, it does not compress so that its density starts to increase. The density is the same everywhere. That is basically what incompressible fluid is. If the fluid starts to relax of some sort in a place, then the density could be less in some places and higher in other places, and that's a problem. So in an incompressible fluid, we're going to assume that this density is the same everywhere of the fluid. Okay, having made those assumptions, it's clear that by conservation of matter for this kind of fluid that is not incompressible is that the area A1 times delta x1, that is the volume of the fluid that just basically was pushed from one side, must be equal to the area on the other side, A2 times delta x2. Assuming it's not 1 second, assuming it's actually delta t amount of time that we're considering, okay? You don't have to have 1 second, because if it's 1 second, delta x1 will be exactly the velocity, because the velocity is the distance per second. But if it's any other time, you just divide by delta t, and now you have the velocities. So A1 delta x1 over delta t is the same thing as A2 delta x2 over delta t. In other words, if I do this experiment in the finite amount of delta t, that this will then tell me, if I take that delta t to go to 0, obviously this will become the velocity v1 on one side, and this will become the velocity on the other side. And these two quantities are equal because the fluid is incompressible, and also this is called the conservation of matter. This is the fact that the same fluid that comes in from one side is the same fluid that comes out from the other side. So this is the continuity equation. That means that the fluid is continuously in here. So continuity equation. So this is the type of fluid that we're dealing with in here. Fluid of this sort that conserves basically the matter that comes in from one side is the same matter that comes in from the other side. Are we clear on this relationship? You will find this relationship very useful for you in doing problems. Okay. Now let's continue with this same fluid now and put it at different heights, okay? So I'm gonna take two sides of the fluid. Okay, trying to exaggerate the sides in here. So this is cross section A. Oh man, cannot draw circle in here. So this is A1, this is A2, and again, this is V1, this is V2, and so we know A1 times A2 is equal to A1 times V1 is equal to A2 times V2. That's something. And also I'm going to assume that the fluid in here is at some height H1, and the fluid on the other side is at some height H2, and the pressure on one side from the rest of the fluid is P1, and the pressure from the rest of the fluid, because you cannot really come up with a with a hose and cut it from both ends and have it hanging, expect flow. This cut is a mathematical cut. This tube, if you wish, or conduit, is part of a big connection, big wire, okay, big somewhere where there is a source of fluid somewhere, and probably it's dumping it to some sort of a sink somewhere, okay? So at this point, we're just taking part of this wire, okay? So that's what we're looking at. That's what P1 stands for, is the rest of the fluid. And P2 also stands for the rest of fluid from the other side, okay? Because that's part of the full picture in here. Does everybody understand that this is not, you cannot have a fluid that runs through this wire like this one, the way I drew it. You have to have some connection here. So this is a mathematical cut, not a real cut. Yes? Okay, at least one person is with me so far. Everybody else. Okay, very good. So this is a mathematical cut, not a real cut. So if you do this, if you take a hose and cut it, you're not going to have flow in here. Okay, you're going to lose flow completely. So you have to do it this way. Now, here is a problem, and I have one of those cases in one of my other classes, okay? So you really, really have to be careful with it, okay? I know some of you are math inclined, and you start to be picky about where in the word are you going to take H, because this whole thing is with respect to a G in here. So we're going to assume that there is some sort of a G in here. What happened in here? So the G in here, that's the gravity. So are you going to measure the height from this height or from here? Where is H1 stands for? Same thing. H2, is it from here or here? What I'm going to tell you about this is that this cross sections A1 and A2 are so small that it doesn't matter where you put it. You can put it for the middle if you care, okay? So A1 and A2 are really small, relatively speaking, compared to the difference between the two heights. So this is a real physical problem. This is not a mathematical problem. And I know some of you are mathematically inclined, and that's actually my background myself. Actually, my thesis was in theoretical physics, so that you know. You have to really leave the math a little behind, okay? And don't start looking at things from these picky levels, okay? Because then you have a problem. You're going to do this experiment even with, and I will tell you a secret, okay, about physics, even with when the difference in heights is not that big of a difference compared to the sizes of the cross sections themselves, namely the diameter of the two cross sections. You will find that the result that we find in here will be very, very good, okay, with the experiment. Now, You want to include that effect. Now, let's say, for example, the sizes are comparable, namely H2 minus H1 is of the same order of diameter D1 and diameter D2, then in this case, you have, I should have put it this way, okay? Then in this case, probably you're going to get into a Taylor of some sort, okay? Taylor expansion of some sort, okay? So that's basically the math thing for it. But for right now, it doesn't matter where you put the height, basically where you're measuring the heights. If you want to measure it in the middle, okay? Measure it somewhere in here, okay? So that is H1, and measure it in here, and that is H2 with respect to the floor, for example, or with respect to the ground, okay? So this distance is H1, and this distance is all the way H2, okay? So that's basically, that is just to give me the gravitational potential energy, that's all in the problem. Because this whole problem is going to rely on the conservation of energy, that's it. We're not going to do F equals to ma. I know I was said that we're going to move into hydrodynamics, and where the word dynamics involves forces or actually energies. So from this point on, we're doing hydrodynamics. The first 2 points basically of this chapter deals with hydrostatics. This one now deals with hydrodynamics. In hydrodynamics, what we're going to say in here is the total mechanical energy at the end minus the total mechanical energy in the beginning is equal to the force of the external forces. And the external forces for this portion of the fluid is just the rest of the fluid, because I'm going to include gravity as part of the mechanical energy. That's it. So the mechanical energy at the end, so think of this whole thing as a mass that is being basically changing its total mechanical energy. On one side, its velocity is one side. And so basically that's in here, it doesn't matter because the fluid is incompressible. So once this, after delta T, the amount of fluid that stays in here, and if this amount is not reached by that delta T, namely that's not part of delta X1, so it doesn't matter because it's going to be replaced immediately. So the velocity is going to be stay the same in here. But the velocity in here, V2, is a lot different than velocity V1, okay? But the velocity in this point in here doesn't matter during the amount delta T. So having said that, let me go back into the mechanical energy. If you guys remember from physics 4A, that E2 minus E1 is equal to the work of the external forces. And in this case, it's the work due to the difference in pressure, okay? External forces. You guys remember this theorem from physics 4A? I'm not saying kinetic, I'm saying total mechanical energy. Oh man, can't see the chat unless I stop here. Okay, good, at least some people do. So we're gonna come back in here and find the mechanical energy. If you guys remember, the kinetic energy, the mechanical energy is the sum of the kinetic energy plus potential energy. So we're gonna come back in here and write this expression, the kinetic energy in position 2 plus the potential energy in position 2 minus the kinetic energy in the lower end plus the potential energy in the lower end is equal to the work of the external forces. Here are the two forces in here. This is doing work. P1 is actually the one that is pushing the fluid on one side. So its work is going to be positive because the force on this side, remember the force is pressure times area. That's what the force is. And area is A1 actually. That's what the force is. So the force and the displacement, delta X1. So the work in here is this much. It's the force, which is the pressure times the area times the displacement. On the other side now, this force is actually on this side and the displacement is against it. So the work is going to be minus the pressure P2 times A2. That is this force in here that we're working against. And the displacement is delta X2. Do you guys see that this is the work? One of them is positive and one of them is negative. From one side, it's doing the pushing, which is the force, which is P1 times A1 times the displacement delta X1, but delta X1, I'm sorry, but we're doing it against the other side, which is the pressure P2 times A2. That is the force, because remember, the pressure is force divided by area. Therefore, the force is pressure times area times the displacement delta x2. Does this expression make sense to you guys? This is simply from physics 4A. Okay, very good. So this is simply from physics 4A. All I'm saying is that the difference in mechanical energy at the end minus the mechanical energy at the beginning is the work of the external forces, and the external forces is coming from the rest of the fluid. On one side, it's pushing the fluid, and on the other side, it's actually the fluid is pushing against the rest of the other side. That's why there is a negative in here, okay? Now, the kinetic energy is just 1/2 times mass times velocity squared, but I have to know exactly what mass it is. So it's 1/2 times rho times the volume on that side. The volume on that side is A2 times delta x2. Remember the volume of this fluid in here that has moved to this side. Okay, remember the expression that I started with? A2 times delta x2 is this volume, because the area A2 times the displacement, in this case, delta x2. So that is the volume. So in this case, so what I have in here is, what is the writing thing? So it's A2 times delta x2, that is the volume. So this is the mass, times the velocity squared, which is V2 squared. Plus, I'm not done with this term completely, so I still have to calculate the potential energy, which is mg times h, and m is the density times, again, the same volume, A2 times delta x2, that is actually the mass, times g times h2, because we're doing this on the upper end. On the lower end, I have to use the same stuff, except I have to change wherever there is 1, I have to change it to, why is it 2 in here? I'm sorry, this is 1. So I have to change everything that has 2 in it to back to 1, because it's the same thing. 1/2 times the mass, which is A1 times delta x1, which is this volume, actually, A1 times delta x1. This is the actual volume, times the velocity V1 squared, and so on and so forth. So minus a big minus in here, open parentheses, 1/2 of rho, it's the same rho, I'm sorry, for the entire fluid. That's a big fuss I made earlier about the fact that this fluid is incompressible, therefore the density stays the same. Delta x1 times V1 squared plus the mass, which is rho, times A1 times delta x1, that's the volume. Density times volume gives me the mass, times g times h1, that's a gravitational potential energy, is equal to that expression, namely P1 times A1 delta x1 minus P2 times A2 delta x2. So what I have in here is P1 times A1 delta x1. This is the force times this. This is the force and this is the displacement, minus P2 times A2 times delta x2. Again, this is the other force times displacement, but the force and displacement in the second part are against one another. The force is pushing one way and the displacement in opposite to it. That's why there is a negative sign in there. Here is the beauty of this expression if you guys look at it. Remember, I just said that the fluid is incompressible. Therefore, A1 times delta x1 is equal to A2 times delta x2. So I have to cancel that term. And let me show you where that term appears in this expression. A2 delta x2, A2 times delta x2, A1 times delta x1 is the same volume. Basically, the volume that came in is the same volume that came out. And the volume that came in is A1 delta x1, and the volume that came out is A2 delta x2. And this fluid is incompressible. Therefore, these two quantities are the same, which is also here too, So all of these terms cancel. So if you guys thought that, what is it, that Infinity War has so many deaths in it, this is very similar to it. There's a bunch of people who die in this case. There are a lot of terms who cancel in this case, and that's good actually, because it makes the expression a little easier for us to write. So let's write everything that has a minus on one side. So these two terms have, but let me first of all clean that A1. So what we are left with is the following: 1/2 of rho times V1 squared, times V2 squared, plus rho times G times H2 minus 1/2 of rho V1 squared minus rho GH1 is equal to P1 minus P2, and everything else is gone. Here is the trick. I have a minus P2 in here. I'm going to move it to the other side. Its sign is going to be a positive. I also have a minus this term and a minus this term. I'm going to move them both to the other side, and they will become positive too. So on one side, what they have is 1/2 of rho V2 squared plus 1/2, I'm sorry, there is no 1/2, plus rho GH2 plus P2, because P2, when it moves to the other side, the sign becomes positive. And now on the other side, I'm going to leave P1 toward the end, but I have a negative 1/2 of rho V1 is going to be positive rho V1 squared plus rho GH1 plus P1. So this quantity is the same in the lower end and the upper end. It doesn't matter where you are. So what this means is that in general, because this 1 and 2 are just arbitrary points, I took them in the fluid. They are mathematical points. They are not real stuff, okay? So what this tells me then that this quantity, no matter where I am in the fluid, is the same. 1/2 of rho V squared, rho GH plus P is constant. Because you calculated in one position, you calculated the second position, and it's the same number. So this is Bernoulli's equation. Very important equation that you guys need in here. Explains many things. One of them that explains for me is the liftoff, for example, in the plane. So if I have a plane, for example, and it's trying to, let's make the wing. Let's see here. I'm going to make a simple wing in here, okay? So look at this expression here. The height is negligible, so I'm going to ignore the height, okay? So what I'm going to say in this case is the fluid, of course, if you are sitting on the plane, if let's say, for example, you're sitting on the wing, this is the wing of the plane, by the way, this is not the entire plane. So this is the wing of the plane. If you are sitting on the wing of the plane and basically you're anchored in it so that you don't fall, okay? So for you, the wing is not moving. So what's going on in here is that the air from the outside is coming to rushing towards you with the speed of the plane. So as far as you're concerned is the flow of the air that comes from infinity and here, and it comes parallel to one another and then meets toward the infinity. So this portion of the air is in this laminar flow. This one actually will go up and come down and meet itself in there. And this one will just rush straight through. Probably I should have drawn these things with different color, but I'm gonna basically make sure that you guys see the wing among all of these things. So this is my wing. Okay, so this is, as far as the wing is concerned, all of this air is coming to rush it. The air is calm, meaning that at this point in here in the air, they're all at the same speed, or they are not moving at all. And then when the plane leaves that thing and disturbed, it's going to leave them at the same point too. Okay, when it meets them, it's going to disturb them a little and they settle down. So which means is that this portion that travels higher distance must travel faster in order to reach the same point in here, okay? With the same, basically, speed, same condition as the previous ones. So V up or V top must be higher than V bottom. This is what I meant by V bottom, okay? So if I calculate the pressure in here, let's calculate the pressure in here, and let's call it the pressure is P top, and this is P bottom. So what's going on in here is 1/2 of rho of the air times the V top squared plus P top squared plus P top squared plus P top, I'm sorry. That's Bernoulli's equation, plus something that is very close from the other one. If you want to, rho G times this H minus the other H. So this quantity, H top, but I'm just going to ignore that quantity and I will tell you exactly why. Rho times V bottom squared plus P bottom plus rho G times H bottom. This H is the same as roughly as the same as this H, so it's going to cancel. Because I'm assuming compared to the big thing, there's a big stream, I'm neglecting that size of the height in here, okay? So that's why I'm going to assume that this quantity is roughly the same thing. And what I'm going to do is find the P in the bottom. P in the bottom minus P in the top. Basically move to the other side. So I move this one to the other one. So it's going to be 1/2 of rho times V to the top squared minus V to the bottom squared. So what's going on in here is that this quantity, because V top is bigger than the velocity in the bottom in order for this condition to hold. So this quantity is positive. That's the key thing in here. This is more than 0. If this is more than 0, because the top velocity is bigger than the bottom velocity, because this is the condition with which the air has to be at the same condition at the end, then this pressure in the bottom is higher than the pressure in the top. What this means is that the pressure in the bottom is bigger than the pressure in the top, which means that this pressure in the low end is higher than this pressure, which means that the plane will take off. You guys understand? So this is how planes take off. When they are in the runway and they put the wing in this direction, the air from the bottom gives you that lift off just by the fact that it's moving with higher and higher velocity. Does this make sense to you guys? Yes? Okay, so actually, if you take this wing and flip it around, that's actually what the NASCAR people do. So they take this one and do it. They put the wing backward so that the car does not take off, actually, when they are doing the racing. So actually, the pressure on the top will be more than the pressure in the bottom, and that will keep the racing car on the track. So that's basically the principle behind it. And that's actually the principle behind also the sinker in baseball and all kinds of applications in here, okay? So if you're a baseball player, it's a good idea to help you to learn these things, because it's something that is that's going to be helpful, okay? In a sense, to understand what you're doing in terms of physics when you're pitching and so on and so forth. Anyway, what time do we have? We still have a few minutes, so we can do another example in here. Hopefully you guys are in the mood for another example, because we're finishing the chapter, by the way. On Wednesday when we meet, we're going to be talking about chapter 15, okay? Okay, the second problem I had in mind is problem 73, which uses this stuff from can you get a piece of paper also and use the other camera instead? Because I like the other camera for this purpose. Or maybe use this one instead of that. Okay. This surface in here. Okay, let me use that instead. This one aside. Where is it here? Take this. Sure, it's not a permanent marker. Dry erase, good. So problem 73. Let me first of all switch cameras. Just let me remove this camera and move the background. Nonsense. Okay, good. So problem 73, okay? In problem 73, basically what it says in here is that a closed and elevated vertical cylindrical tank. So the tank is cylindrical in shape. So hopefully I will be doing a lot of racing, so you guys need to follow through, okay? So, so I have a cylinder in here and it's elevated, some sort, okay? And with diameter 2 meters. So this diameter is 2 meters, okay? And contains water to a depth of 80 centimeters. So we can take the top in here, but we don't. Let's say, for example, take this is the fluid, and that's water actually. So this is water, And this height in here is 80 centimeters, 0.8 meters, okay? So we know the volume of the water that is contained if we're really interested in that. A worker accidentally pokes a circular hole with a 0.02 meters in the bottom of the tank as the water drains from the. So basically, it comes in here and pokes a hole that is diameter D equals to 0.02 meters or 2 centimeters. Okay. So that's basically what this thing. Of course, the fluid starts to flow in this case. It's going to start to come down. Okay. So it's no longer static. It's not starts to be dynamic. Okay. As the water drains from the tank, compressed air above the water in the tank remains at gauge pressure 5,000 Pascal. So the gauge pressure, which is very, very important that you have to understand that the expression earlier we talked about was there is a difference between the gauge pressure and the absolute pressure. So we're not talking about the absolute pressure in here in addition to the atmospheric pressure. So this is just a difference in pressure between this point and that point. So the gauge pressure is 3,000 PG, if you like, in here, is equal to 3,000 or 3 kilopascal. Okay. 5. I'm sorry, 5. Why am I saying 3? 5 kilopascal. Okay. At the surface of the water, ignore any effects of viscosity. Just after the hole is made, what is the speed as it emerges from the hole? We're going to use Bernoulli's equation. Okay. What we're going to say in this case is, first of all, the continuity equation that gives me A1, which is this area, which is pi times this diameter squared, is equal to times the velocity v1. This is the velocity v1, or the top, if you like, must be equal to A2 times v2 in here. So this is one relationship that links the two velocities in here. So this is A2. So A1 is pi d squared over 4, if you like. And A2 is the same thing as pi d squared, the little d over 4. Remember, we are given diameter. We're not given radii. Okay, so we have to divide that by 2 when square it, we're dividing by 4. Okay, so we got this relationship between the velocities. We also know Bernoulli's equation tells me that 1/2 of rho of this water, so we know what the density is, times v1 squared plus rho times g times h, and h is exactly 0.8 centimeters. Okay, if we calculate from this point in here, so h for the other side is going to be 0, okay, from this height, is equal to plus the pressure, plus the pressure P1 is equal to 1/2 of rho times V2 squared plus rho GH, and H is going to be taken 0 because I took A as the origin of the axis in here, okay, plus rho G times 0 plus P2, okay? From this expression, we're going to be able to get rid of one of the V's, since we're asked, what is the question that we're asked again? What is, just after the hole is made, what is the speed of the water as it emerges from the hole? So we want to know V2. If I equate these expressions in here, that means that pi over 4 times d squared times V1 is equal to pi over 4 times d2 squared is equal to times V1 V2. I can find what V2 is in terms of V1 and sub in this expression. H is 8 centimeters and the difference in pressure, so we should be able to get this expression. But before I do that, let me get rid of this constant, okay, because it's the same everywhere. So V2, or if you wish, V1 is equal to D over D squared times V2. But D over D2 is just 1%. because 0.02 divided by 2 is 1%. When you square it is 1 to the power 10 to the power negative 4. So this quantity in here is 10 to the negative 4 times V2. So this V1 in here can be ignored. Since this V1 squared can be ignored in front of V2 squared. So the expression then, I'm going to ignore it because of this rationale in here, because this is coming from the continuity equation. So the continuity equation will dictate that this velocity V2 is a lot bigger than this velocity, because this one is a much, much bigger area. So if it drops a little, it's going to drop a little compared to this one that is coming very far, very fast. Again, it's coming from this relationship because the areas are completely they're in proportional to one another. I mean, one of them is a lot bigger, namely A1 is a lot bigger than A2, so V1 must be a lot less than V2, basically. And that's how the order of magnitude is, because the ratio of D over D is 0.01. When you square it, it's going to be even less, 10 to the negative 4. So this expression I'm going to neglect in this term. So V1 squared is going to be roughly 0. Just to get an estimate in here, for you, part of the task is to actually calculate. That's item 2 of the discussion today, is to finish the calculation, okay? Because I'm not going to do the numbers. I'm going to just show you how this problem is going to be done. So, by the way, anything we do in class, in addition to the homework, your guys are responsible for in terms of exams. So you really need to know how to solve these problems, okay? So this is part of your review for the exam. So let's do this thing in here. So rho V1, 1/2 of rho V2 squared is equal to, this is 0, rho GH. So it's going to be rho GH plus P1 minus P2. And that is the difference in pressure between the high level and the low level. And that is the gauge pressure. That is 5,000 kilopascal, basically. Okay. And this expression rho is water is 1,000. Or we can use whatever units that you guys are comfortable with. We can go back into, since it's given in Pascal, it's a good idea to measure everything in terms of meters. So this is 0.8 meters. Rho is 1,000 kilograms per cubic meter. Rho is 1,000 kilograms per cubic meter. And from here, you should find an expression for V, which is just the square root of rho GH divided by 1/2, which is 2 times. Rho cancels rho. So I'm left with the GH in here, okay? Plus this number divided times 2 times P1 minus P2 divided by, what is it, rho. And that is the expression that I'm going to find. I expect that you guys check my algebra and also plug in the numbers. You have G, which is 9.8. You have H, which is 0.8. P1 minus P2, which is 5,000 Pascal, or 5 times 10 to the power 3. And this one is 10 to the power 3. So cancel 10 to the power 3 and the 10 to the power 3, and you should be able to find the value for the velocity. Okay, so that's part 1. Okay, does this make sense to you guys? Yes or no? Okay, so let's discuss part 2 in here. Part 2, it says, B, what is the ratio of this speed to the flux speed of the top of the tank is open? Okay, so we're going to find this one in here. If this top is not sealed, actually, and it's open, so it's atmospheric pressure now, P atmospheric in here, P ATM. And on this side, it's P atmospheric also, because it's an open on both sides. So the gauge difference in here would be 0. So this number will be 0. That's all. So we're going to find, so V2, when the case it's completely not, we're going to be roughly this number. So we're going to compare these two ratios, okay? So this is going to be slightly higher than this one. When there is a gauge pressure, when you're pushing more on it, that's what the gauge pressure is. So it's going to be slightly higher than when it's in open air. It's going to run slower, actually, in this case, okay? Does this make sense to you guys? Yeah, so when you have, because initially we have a pump in there, so it needs to run faster. And that's how by how much faster it's going to be, by the gauge pressure, basically. Okay. How much time does it take for all the water to drain from the fluid? What time it is? So now we have to do a little bit of work in here, okay? So this is initially after, that's why I use the expression in here, H equal to 0.8 meters. This is after we open, after the guy accidentally punched that hole. But if we wait a little longer, this expression now becomes dynamic because H is changing with time. And the rate at which it changes is actually V1. Let me erase somewhere in here. Let me go back into this expression here and rework it, okay? So H is a function of time now. And the rate with which it's changing, namely V1, that is the velocity with which it's moving down. So V1 is equal to dH over dt. Remember, V1 and V2 are related to that expression, namely A1 times V1, which is dH over dt, by the way, is equal to A2 times V2, okay? And V2, we found it from the previous expression. It's going to still hold true. So we're going to find dH over dt equals to the ratio of the areas. So I'm going to write A2 over A1. This is small number times the square root of, what was the V2? 2 times GH. Please check my algebra in here. Plus 2 times the ratio, the difference in pressures, P1 minus P2 divided by rho. So this is the expression that we have in here, okay? We want to know the time when this whole thing drags to 0. So what I'm going to do in here, I'm going to move dt on one side and move dh on the other side. So I'm going to find dt equal to dh over this entire thing. dh, so this is a scaling factor, so I'm going to leave that one in there, but it's going to flip around. So it's going to be A1 over A2 when I divide by it. So it's going to be dh over the square root of 2 times gh plus 2 times P1 minus P2 over rho, okay? So that is the expression that I have in here, okay? Here is the deal. I'm going to integrate from h equals to 80 centimeters, or 0.8 meters, down when h is equal to 0, when we're completely drained this thing, okay? So those are my boundaries of integration from the other side. The integration from t is from 0 all the way to the time t when this thing is drained. So on one side, I will find big T. On the other side, the integral starts from 0.8 and comes down to 0. And I'm going to integrate this square root of h in here. So all I have is an h in the denominator, and make your change of variable and take the power, the integral of x to the power 1/2, and so on and so forth, okay? So again, the item 2 of the discussion, you need to finish this problem. And once you do that, once you plug in all the numbers, you should find the finite value of t. I don't know if it asks this question. What is the ratio of the? Oh, yeah, it did. So again, they want to know if the gauge pressure is open, basically this is 0. How much time it is? Obviously, the time will be shorter when there is a gauge pressure than when it's open, because when it's open, then it's going to fall by itself and it's going to take a longer time. So if I do it without this term, I should find a longer term than if I do it with term in. So I'm going to find two values in here where this is 0 and when this is not 0. So the first question is when this is not 0, all I have to do is integrate the expression dh over something, h plus something in here, make change of variable and do all of the things. So you should be able to find the expression here. Do you guys understand how to handle this problem? Yes? Okay, at least I have one person. Remember, this is part of the items for the discussion. You're supposed to finish this problem, okay? Okay, very good. So guys, I'm gonna see you guys this afternoon. I know I have 1 minute to spare. So if you guys have any question, you can ask it now if it's a quick question. If not, we have a meeting this afternoon at 2 o'clock.
Oh, Professor?
Yes.
So when you said for the Excel, right, how we just have to understand how to do it, how do we like reference that in our discussion post?
Basically what we discussed, okay, what I said earlier. You need to be familiar with it and learn it and things like that. So however you put it, it's in your own words.
Okay, all right.
Okay.
Thank you.
There is no thing wrong with the which way you do it, as long as you get the points.
Okay, thank you.
Very good. Okay, it's 10:25. We're really right on the time, so I'm gonna see you guys this afternoon. I hope to have this recording ready for the other class, for the other people who are not in here. And there are only 3 people who are not here. Hopefully they will not miss much also, but they will really need to be attending too. Okay, see you guys around. Let me stop the recording.
Professor.
Thank you.